just introduce our last gentleman speaker, Raj Talluri, who's SVP and General Manager of the Mobile Business Unit at Micron. Previous to that, he was at Qualcomm. He's going to come up and tell us around this world of AI, some of the new processor architectures and system architectures we're seeing in these new systems. So with that, Raj.
Okay. So can you guys hear me okay in the back? Mic's good? Okay, awesome. So what I wanted to do today was, talk to you guys about, some of the popular DNN architectures that are out there, and what you should think about in terms of what's the architecture, what's the processor you should use if you got this burning machine vision problem, burning neural networks problem, an AI problem that you want to solve. Before I did that, what I wanted to do is actually spend a little bit of time, maybe 10 minutes or 5-10 minutes, talking about how I look at these problems and how are they different from normal compute problems that we've used to seeing. So first, what I wanted to do was I wanted to get us all on the same page in terms of taxonomy. Okay, so this is actually from John McCarthy about how you classify AI versus machine learning, and then machine learning is really a subset of AI. Long time ago when I did my PhD at UT Austin, there's a big AI school, and everybody talked about AI being, early 90s. And then there was a smaller machine learning team there that worked on machine learning. Now, a lot of people use machine learning, AI, neural networks, deep learning, all interchangeably. But I kind of wanted to put this slide out there, maybe obvious to many people, but I did want to get us all on the same page that, deep learning and spiking, these are, brain-inspired machine learning is actually what covers those two. We don't really know if brain works like a neural network, but that's the conjecture. And deep learning is actually part of the neural networks. And the reason it's called deep learning is because the networks are actually deep. So there's just a whole bunch of layers, okay? So let's get everybody on the same page on that one. Lots of applications for machine learning, right? I don't really need to spend too much time on it. Object recognition, video surveillance, autonomous navigation, online shopping, recommendation engines for the kind of video you want to watch, medical diagnosis, new drug creation. Just every day I find like another different application for which you want to use this, which is kind of interesting to think about that these are so disparate and wide, but people use the same compute paradigm. And that's something that's very interesting about these kind of architectures and what has happened in just the last few years, right? So I'm going to click through the first few slides a little bit quickly because I think you guys probably know a lot about this stuff. But I did want to present them because I want us all to be on the same page. Basic neural network computing model, there's activations that come in the input, and then there's a bunch of weights that you multiply them by, and there's a layer in the middle, which we call the hidden layer, and then the output tells you what the thing is. And based on how many of these layers you stack up, you can talk about how deep the network is, right? And how wide this is basically based on how complex the network is and what kind of problems you can address. So the inputs, people call them activations, and the weights, are the synapses. That's kind of where the brain-inspired part comes a little bit, because that's kind of what people use for neurons in the brain computing, with the weights being synapses and activations being the signals. These networks are used both for training and inference, and that's an important element. People use these networks to train based on a whole bunch of data with ground truth, and then get the networks, load them onto the edge, and use them for inference. I'm only going to talk about the inference at the edge part today. I'm not going to talk about the training part, because that in itself is a fairly large area to cover. And typically, you use backpropagation to modify the weights till you get the network to learn what it is, whatever it is that you want it to learn. Now, there is a fundamental difference between how DNNs are and how typical workloads are. So DNNs, because, and by DNN I mean the deep neural network, you can interchangeably use it for neural network with a lot of layers, they become commercially very important. I've been coming to this show on and off for the last few years. I just spent an hour outside walking around. It's pretty impressive. You guys are just coming from the showcase. Pretty impressive, the kind of applications you see. A whole bunch of real products, real applications, and I still think we're just barely scratching the surface of what can possibly be done with this. And it's very nice to see some real applications. So they're becoming commercially very important. Now, the DNNs represent a very different type of workload, and that's actually a very important point. So if you're trying to, I don't know, put numbers in ascending order, or you're trying to do a search, or you're trying to do a H.264 computation, or you're trying to do speech processing, they're very different from how you do a DNN processing. So they're fundamentally different workload, and that is something that I think those of you who are trying to decide which processor to use need to kind of accept and understand. The workloads are big, but they're very uniform and parallelizable, and that's an important point. And then that's why people believe that you can make a specialized processor and get a lot of lift for it. So I'll just flash it out there. A lot of the stuff on cloud versus edge. Cloud, typically where you think training is done, and edge is where the inference is done. When you think of edge, think of your smartphone doing some stuff, or your surveillance camera. When you think of cloud, you think of a big server in the cloud that's being trained. I listed a few things here about what's done on the cloud versus the edge. Training and inference are both done on the cloud. Mostly inference is done on the edge. So I'm going to focus this processor architecture conversation about the edge and about inference, not about training, okay? It needs to be real time, and we heard some of the talks today about low latency. It can be integers or binary. Battery is very, very important because most of the edge devices are battery operated. One of the largest platforms that we'd like to do machine learning in is your cell phone. 1.4 billion phones shipped a year and maybe more. They're all battery operated. So it's very important that we actually figure out what kind of architecture takes the least amount of power. And the resources are limited. The amount of memory in a battery is limited. We at Micron want you to buy more, so the phones get bigger, more memory, but So moving on to convolution networks. A class of networks, of the DNNs is actually the convolution networks. And convolution networks are a very important class of networks because what these networks are implementing is basically a convolution. And those of you who are familiar with image processing or signal processing, signal processing one-on-one, you understand the concept of convolution. Essentially, you take a filter, you take an image, you take this filter and put it on top of the image and do point-wise multiplication of every pixel on the little block and the corresponding pixel on the image. You add them all up, and you get one output. And then you slide the guy a little bit, do it again, do it again, do it again. This is actually the heart of the processing that's done in the convolution networks. And it's very important to kind of realize that this is what all your networks are trying to do, is to do an image convolution. There's some variations of this, and this is something, for example, that's used in image recognition, or all the demos I saw outside of autonomous navigation. You're trying to do lane detection. They're running convolutions. They're running image convolutions again and again and again. There's a few differences. You can have a bunch of filters that run on the same image, and you can have a bunch of channels that. So for example, the RGB can be 3 different channels. You could have a different high-pass filter, low-pass filter, different kind of filters that you run. Those are the filters. And as you apply a convolution for an image, you take an image, you apply convolution, output comes out, and you do it again. And every time the new output comes out, it's going to be a higher level of abstraction than what you did before. So for example, if you just took this picture and applied a convolution, it generates a feature map. The feature map on one level higher in the network will probably just be edges. You do it one more time, edges will get into groups of similar things that make sense. And hopefully at some point it gets into features that really make sense, and you can say it's a lane or not a lane. And that's kind of one way to think about convolutions. And the reason I'm spending some time on this is convolutions can be implemented as matrix multiplications. That's kind of the fundamental aspect of a convolution. So you probably know that if you convolve in the image domain, it's same as multiplying in frequency domain and so on. So basically, the way people implement convolutions is through multiplications. And when you implement it as a multiplication, so it's really a matrix multiplication that you're trying to solve. So almost all processor architectures that we're going to talk about, it's about how do you do a matrix multiplication efficiently. That's what it boils down to. So while there are many, many different networks and people talk about all these complex networks, the heart of the matter is how efficiently can they do matrix multiply. And that's what is going to help you decide which one should you use. And inside a matrix multiplication, the fundamental element of computation is a multiply and accumulate. So essentially, you take an input, you multiply it with another input, and you get the result, you add it, and then you cast it to memory. So this is the heart of the computation in all DNNs. Now, if you look at this, a couple of comments. One, the inputs, 2 inputs come from memory on the left side there. So you can see those 2. And then you do a multiplication. Then you add, then you get another input. You add it. and write it to the memory. So basically, there is 2 inputs at the top, and third one, and this one. So there's actually 4 memory accesses for every time you do a multiply accumulate. What does that mean? It means the bottleneck in DNNs is really the memory access. And I think I was chatting with some other people before. So the fundamental problem really is how fast can you access a memory? And that's the difference in all these architectures is how do you make sure that the memory accesses are done fast enough that you can actually get to do what you need to do. Now, some of this material is actually from a very nice paper. You guys should read it. It's called Efficient Process of Deep Neural Networks, a tutorial and a survey by Vivian Z and her team at MIT. They did some beautiful and a very nice paper that I've seen recently, and I borrowed some of this from there. This actually is an interesting slide, and I do want to spend a little bit of time on this. So the way most architectures that you see that people implement today come about is they have a global buffer. So they get the data from the DRAM, store it in the buffer, and then they have a PE, which is like a processing element. It really has some local memory in it, and an ALU, which has no local memory. So if you look at this, if 1 is the reference of how much time an ALU takes to compute, if you had a register file, which is where all the input parameters are stored, and the register file is inside that PE, so to move from the register file to PE is the data time, now it takes that as a reference. And now, if you have a network of things, then it takes 2 times that, because now we are having to move from the processing element to the ALU, not from the register file. That's 2x. If you had to move from the global buffer, it's 6x. And if you actually had to move data from the DRAM to the compute engine, it's 200x. So this actually shows you the problem of implementing DNNs with memory accesses. So the closer you have the memory, the faster you can compute this, and further the inputs are stored, the more it takes. There are 2 kinds of architectures that have become quite popular. One is what I call basically temporal architectures, and the other is called spatial architectures. And the temporal architectures essentially mean that they stagger computation in time. So if you look at, for example, this one here, all the ALUs have access to the memory, and they have the same control. So every ALU is going to perform the same function at the same time coming from the memory. And the control signal tells you do this. So this is typically what happens in a SIMD machine or a multi-threaded machine. So if you look at DSPs, our ARM processors, our GPUs, this is what they do. They do the same computation on all the data with 1 command. Whereas these kind of architectures, are actually what I call spatial architectures in the sense that they're distributed spatially, so the ALUs can communicate with each other. So this time what happens is, if you look at this convolution, you compute one, and you can send it to the next element and to the next element. But in the other architecture, you compute, and you have to write it back to the memory. So these are typically a lot more power efficient, and this is where all the specialized architectures are. So if you actually look at all the specialized architectures that you see here, in some form or the other, they're doing spatial stuff. If you look at the more not so custom architectures, they're doing temporal stuff. Okay, you guys still with me here? All right, so now I'm going to talk about what are all the things out there, and how do they fall into 1 or 2 of these categories, and how does someone who's got a machine vision or a DNN problem to solve think of what architecture to use to solve that problem. And that's, I think Jeff mentioned to me, there may be a lot of people here who are actually, engineering managers and people like that are having to, deal with this decision of people coming in and saying, hey, what processor should I use? Or maybe your engineers are saying, I want to use the Qualcomm guy's processor versus I want to use Mythic Computing. Or how do you want to think about it? So I'm going to spend a little bit of time on that. So today you can get GPUs, CPUs, DSPs. NVIDIA Jetson is a class of a GPU. The Intel CPUs, Adreno, ARM cores, TIC6X, Qualcomm Hexagon. These are all DSPs and GPUs and CPUs that you could buy for a problem. And they're all basically temporal architectures. So they execute temporally. Same command, boom, boom, boom. In time, it'll actually get to the solution. Now, the specialized processors, and I kind of, again, if one of you guys are in a startup and I didn't put your name here, it's not because I don't think it's important. I just did a quick survey, and these are the ones I found, and I put them out there. And I think someone was saying there's 75 startups funded in the last 3 years on specialized machine learning architecture. So, but they're all trying to do something similar, which is how do you address the problem as a spatial compute problem instead of temporal. Then there are the mobile SoCs. As I mentioned, 1.4 billion cell phones sold. So the cell phone guys have been trying to solve this problem of how to do AI and machine learning in the phone. And one of the most popular applications, is picture taking has become a very popular application in cell phones. People like to take pictures and share them. And one of the problems of taking a picture with a cell phone is you don't always get the right picture that you want because the phone doesn't really know what you're taking a picture of. So if you're taking a picture of someone moving fast, the shutter speed has to be really high. If you're taking a picture of, nighttime, it has to be different. If you're shooting at a beach, it should be different. And traditional cameras had this button called the scene mode, which I don't know any of you use. Nobody actually use it that I know of. You keep changing to where you are and take a picture. They all put it in auto and shoot, and you never get the right picture when you want it. But what's happening now is the phone companies have figured out a way to actually use AI and machine learning and this kind of concept of convolution networks to actually figure out what are you taking a picture of. Because they can recognize the scene and figure out what that is, and they automatically set the parameters of the camera to take a good picture at that time. And that's one of the big applications that kind of drove a lot of the mobile SoCs to actually add some form of DNN computation into the SoCs. And Qualcomm, Samsung Exynos, HiSilicon Kirin, MediaTek Helio, these are all examples of that, of doing that. And I'll talk a little bit about that. Then there are the FPGAs, where you actually don't exactly know what you want, but you can put different forms of compute into that, and they're a lot more programmable. And there's interesting computing in new architectures, like this one I found called Mythic, which actually does a lot of the computation actually in the analog domain instead of doing it in the digital domain. So what I'm going to do next is talk a little bit about each of these and give you some insight into my personal view on what processor you should think about for what application. General purpose CPUs and GPUs. The thing about these things are they're the most flexible and they're good for a whole variety of both AI workloads and non-AI workloads. So if you went and bought an NVIDIA Jetson or you went and bought an Intel CPU, you can use them for a lot of different things. They have lots of extensive software. So the other thing I want to mention is that nowadays with Café and with Torch and a whole bunch of networks, frameworks out there, it's important what frameworks are supported by the processor you're going to choose. Because you don't want to manually code this process to your network. It's really painful. So you actually want to have a trained network that you can import into one of these Café or on TensorFlow and then have it automatically optimized to the specifics of the architecture. So what support you get on each of the processors varies. So I would encourage you to first look at what's the support you're getting in terms of architectures, in terms of platforms that you could use and software frameworks. You get most of them on these general purpose processors. And I looked at the NVIDIA website. It's amazing what they've done with CUDA. You could just pretty much get any of that stuff and quickly load it. Intel has got some now. They are going to be much higher power consumption because by definition, because a lot of the hardware that's in there, it's not being used optimally. And as I talked about it, these are mostly temporal architectures. That means the ALUs don't communicate with each other. That means every time they're going into the memory and coming back after you do a computation. And as I showed you, that causes a lot of the power because going to DRAM and back or a buffer and back costs a lot. But they're readily available. I mean, you can get, I just did a little Google search, and you can get a lot of these platforms very quickly and start getting going. This is an example of the NVIDIA Jetson. Again, they use the Tegra processor, which is one of their mobile processors, but they put a whole bunch of stuff around it and to make it easy to use with the different GPU UIOs and different things to connect to, display, PCIe, SATA. You can get the platform very quickly, get started, and they provide you this terrific framework of how to actually have all these things. But it's interesting here to see that NVIDIA really supports all these things on the GPU. Their whole goal is to have Café, Torch, TensorFlow, all of that run on the GPU. And you'll find that a little bit different from the other mobile processors where they actually map that not just to the GPU, but to the other compute elements also. So if you go to ARM, actually it's off there. Again, all the information I'm presenting here is public domain. I pulled it off their websites, just putting my twist on what I think they are, right? ARM now has a very good ecosystem of software offerings that they have, as you can see there. And there's a bunch of software products. And what they're trying to do here is to provide an abstraction layer so that you can actually run it either on the ARM CPU or the GPU, or this is not fully supported yet. And they now have an ML processor also that you can license from ARM. And when you get a workload to run it, you can run it in any one of them, and the software abstracts that. Now, typically, when you run your workload on a CPU or a GPU, it's going to take more power. but it's a lot more flexible. If you run it on one of these NPUs, it's going to take less power and run faster, but it's not as flexible as what you can do. So that's the important decision you need to make when you actually figure out where you want to do it. Now, the software will abstract where it runs, but the power numbers will be very widely varied, as I showed you in the previous slide and what the issues are. This is their ML processor. As you can see, there's a Mac engine, there's a programmable layer, local memory, network control unit, DMA, external memory. Hopefully, these things make sense with what I showed in the last slide. Really get the data from outside DMA into the local memory, use the programmable engine to control it, do the max there, right? That's how these things work. Now, mobile SoCs. These are pretty versatile for a variety of AI and non-AI tasks, just like the CPUs and GPUs. They have good support. I wouldn't say great support compared to like a general purpose processor for most of the popular ones. And you can look at their websites, Qualcomm and HiSilicon, Samsung, they're adding more and more. But it's not that easy to get these development platforms. And they've got one or two, but if you really want a lot of development platforms, easy to use, get started, typically it's harder because a lot of the investment from mobile companies has gone on Android. So mostly you're going to get an Android development kit or maybe a Linux, but not as general purpose as you just get a CPU or a GPU. So that's a little bit harder. They're going to be a little more challenging. They're going to take higher power than a specialized processor. They will take a higher power. But it's going to be less than a CPU or a GPU. There is another difference in a mobile processor, which actually is shown here in the Qualcomm 845, which is again one of the presentations of the Qualcomm website. Qualcomm processor actually has a DSP, which you can think about as a multiply, accumulate accelerator, because it's got multiple things it can do. And it's got CPUs, and it's got the GPU. What Qualcomm has done is it's kind of added another thing called hexagon vector extension. So it's an extension to the DSP, but it has a bunch of more MACs that you can control. But again, they all execute the same instruction when you do it. So they're still very temporal in how they operate, and they don't communicate between each other. So you have to go back to the memory and come back in to process that. But you can take your AI task, and you can run it on the DSP, or you can run it on the GPU, or you can run it on the CPU. And what they've done is, to make it easy for you, they've kind of provided a whole bunch of this thing called the neural processing engine, which is a software abstraction to let you take your trained networks in one of these software platforms, get it in, and then just map it to those based on whichever is free. Because you also got to remember, a phone's doing a lot of other stuff. Like, the CPU could be running the web browser, the DSP could be playing audio. Now, if you want to do some machine learning, those resources may not be quite available to you, so you have to figure out, is the DSP free, is the NPU free, and so on. And some of the newer processors actually from these companies actually have some dedicated hardware to do this kind of computation. And these are all the applications that Qualcomm claims these can be done. Very similar to the MediaTek Helio. I actually just saw outside MediaTek demonstrating their Helio platform. Very similar with the Huawei Kirin processor from HiSilicon. That actually has a neural network hardware engine called NPU, which they licensed from Cambrio, which they actually put in there. MediaTek has a hardware engine, and Samsung Exynos has one, so on. Now, the next thing I want to talk about is actually a broadcast of specialized hardware for doing DNN processing. The whole goal of these things is they're actually going to be most efficient in terms of power and in terms of highest performance you'd get. They all provide fairly good support now, but not as flexible as the other ones. And the other problem is, a lot of these things I find now are mostly from startups that I've seen. Now, there are IPs you can license from Cadence or ARM. So they can be, the support may be a little iffy, right? I mean, you want to get a whole bunch of, let's say you wanted to get software platforms, you wanted to get development kits, you want your whole team to start working on it. You kind of have to, figure out, it's not like getting Jetson development platform or Intel CPU or a Qualcomm processor. So you're a little bit more limited in that. But you're going to get tremendous amount of power advantage, as I told you, because what they're going to have is they're going to have a little bit more memory closer to the compute engine, and they're going to have faster access, and they're going to have good communication between the ALUs, so the data actually flows spatially instead of temporally, so you get that lift. Now, many of them actually use these things as an accelerator. So you actually use a general purpose processor to do some of your computation, and you buy one of these startup kits from one of these startups, or and then use it as an accelerator. So, for example, Intel Movidius comes as a PCIe card you can plug into your PC. So that's the other way people try to do is add this as an acceleration. So this is actually, again, this great paper I talked about from the MIT Iris team. I didn't want to put any of the block diagrams of one of these startups, a little secretive about what they do. So I actually wanted to just pull out this slide from the MIT website. This is very typical of how people implement. So if you think about it, you've got a bunch of off-chip DRAM. You take it out and you decompress that. You store it in a local memory, and then the local memory, will send that stuff to the ALUs, and the ALUs compute it, and they can communicate among each other. And then they write it back, the partial sums. And for the next operation, now it becomes filtered output, because I told you it's convolution. So first time when you get an image, next time what you're going to get after one operation is going to be features. So that's actually the F map. That's the feature map that goes in. You do one more time, and then it comes back out. And what you did in the previous time is the partial sum that goes in. And you just crunch it for a while, and you come back out, and you apply typically like a ReLU kind of operation to do the nonlinear stuff. And then you compress it and send it back. That's basically what these things do. And almost every processor, I've looked at a bunch of them. There's a lot of difference in terms of how much memory is locally here, how many units are there, how do they communicate with each other, that kind of stuff. But they basically all do something very similar. OK, I'm almost out of time. I'm just going to spend a couple of minutes on this slide, and then we'll wrap up. This is another interesting thing that came from Mythic Computing. And what this does is very interesting. It actually does computation in analog. So you take an analog signal, you apply a digital to analog conversion, and then essentially you use the Ohm's law, and what you do is that G there is a conductance. So essentially you get the voltage and the amount of current that flows through, because of the conductance, the Y is called VG, and you get a multiplication there. So that at that particular node there, you get the multiplication effect. And you take a bunch of them, and you put an ADC and take it out. Now you get a multiply accumulate. So now you're able to implement a multiply accumulate in analog domain. Very interesting application. Again, a little bit more specialized. Support structures are going to be a little different, but they're going to be extremely power efficient. So that's my last slide. If you guys are in the business of choosing a processor, you first need to figure out how much important is flexibility to you. Are you going to do some general purpose computing? Are you going to run different kinds of network? And so on. What all DNNs do you need support for? How many frameworks do you need to support? What's the accuracy of this? So the larger the machine and the more stuff there is, the more accurate the networks are. How much power and energy is it going to take? Are you battery operated? Are you plugged into a wall? It's something you want to think about. Latency is another important thing. The faster you execute something, the faster you can come back. And if you take a little bit of latency, if your application can handle it, then you can choose a different one. Cost is a big deal. How are you doing this at scale? If you start using FPGAs or expensive mobile processor, you're going to be paying for stuff that you may not really need. So you need to think about that. And are you going to ship this in high volume? That's another area that you need to. If you say, if it's thousands is one thing. If you're going to ship millions of units of it, then you kind of have to, this cost and latency become more of an issue for you. And what are your support requirements? How long do you need this thing to be in the field? If you went and bought something from a startup and you want it to be there for 20 years, you kind of want to think about that, because there's 75 startups out there. I don't know how many will last. So those are like the top things. And that's actually my last slide. And I hope you found some of it useful. Thank you.
Right. Any questions for Raj? I'll start with one. Evaluating performance.
Yeah.
Right. So you talk about some of the requirements there. What do you, maybe just while we got you, what are your thoughts on, what are you seeing people use? The infamous TOPS, ResNet, MLPerf. How do you, again, guiding the audience as people sort of think about performance, what are you seeing as the right way to do it?
Yeah, I mean, clearly, I think the first level of analysis you need to do is, the TOPS does provide a number for how much can it do, what is the ResNet performance. I think you do want to use that as a guide to start, but really it's going to depend on your application, and accuracy is another big deal. So, you can get certain level of performance, a certain level of accuracy. You can run more, but your accuracy falls off. So you want to balance accuracy and latency and performance at the same time. And the other thing you really want to think about is, what is your application? If you're really running convolutional networks on images, I think is one thing. But if you're going to do a recommendation engine for the Netflix movies you watch, it's a different. So you have to kind of think about what's the application, what's the accuracy you need, what's the latency you need, after you make your TOPS decision.
Right. Any question? Yeah. Good timing of a good stand-up there. That's good.
Hey, Raj, very insightful presentation. Really enjoyed it. You mentioned a lot about sort of performance gains you could get through hardware architecture optimization, such as bringing the memory closer to the ALUs, using spatial architectures. Do you have a perspective on performance gains you could get through software, particularly, say, on the lower level, the compiler, the assembly type of, to get another competitive edge if you're one of these 75 AI startups?
Yeah, yeah, for sure. I think I was just talking about the elemental computation advantage that you can get from the architecture. But once you get that, you actually have to really focus on the software side. Particularly, I didn't talk about things like pruning or pooling or things like binarization. And so there's so many other elements to actually the computation instead of computing everything. So I think that the software is the next level of thing that really you need to spend some time on. And I find that different companies have optimized different amount of software optimization to the architecture. And that's probably something you also want to think about, whether you have to do that optimization or you get it from the company. Yeah. A good point.
Any last questions for Raj? If not, thank Raj. Thanks
Thank you.
very much.
My pleasure. Yeah.